Welcome to today's Explainer, everyone. Today, we're diving into something really fascinating, the physics behind how things rotate. We're not just looking at how things move in a straight line anymore. So if you've ever stopped to wonder about the hidden mechanics of everyday objects, you are absolutely in the right place.
Here is a quick look at our roadmap for today. We'll start with number 1, what is a turning force? Then we'll hit 2, the math behind the moment. After that is 3, the rules of equilibrium, followed by 4, center of gravity and stability. And finally, number 5, real-world physics in action.
All right, let's jump right into section 1. What exactly is a turning force? Up until now, your studies have probably focused a ton on linear dynamics. Things moving straight forward or backward. But we're shifting gears today to the equally important physics of rotation. And to really get this, let me ask you a quick question. Why is it so incredibly hard to push a door open if you press right next to the hinges, but practically effortless if you push out by the handle? Have you ever actually stopped to think about that everyday mystery?
Well, the secret to that little mystery is our main concept for today, the turning effect of force. When a force tries to rotate an object around a fixed point, it creates this turning effect. You'll actually see this referred to in your textbooks as the moment of force. The big takeaway here is that a force doesn't just push things in a straight line. It literally has the ability to make things spin.
Moving right along to section 2, the math behind the moment.
So how do we actually calculate this? It's honestly a beautifully simple formula. The moment, which we call m, equals the force, F, multiplied by the perpendicular distance, d. So m equals F times d. This little equation tells us exactly how much rotational ability a given force has. And since we're multiplying newtons of force by meters of distance, our standard unit is simply the Newton meter.
And this right here is exactly why that door handle trick works. Think about it. If you push near the hinge, you have a very low distance, which means you have to apply a massive high force just to get enough moment to open the door. But if you apply a low force at a high distance, like out by the handle, it generates a large moment, making the rotation super easy. The distance is literally doing the heavy lifting for you.
Now, we do need to be super precise about one thing. That d in our formula isn't just any random distance. It is strictly the perpendicular distance from the line of action of your force straight back to the pivot. And the pivot is just the fixed point around which the object rotates. So in our door example, the hinges are your perfect pivot point.
Which brings us to section 3, the rules of equilibrium.
Okay, so what happens when you have multiple turning forces acting on something all at once? Well, first, we have to recognize that forces can rotate objects in 2 opposing directions. It's exactly like reading an analog clock. A clockwise moment rotates the object in the same direction as the hands on a clock, and an anti-clockwise moment pulls it right back the other way. It's basically a constant invisible tug of war.
And this tug of war sets up a massive rule in physics called the principle of moments. This is crucial for your exams, so read it with me. When a body is in equilibrium, the sum of the clockwise moments exactly equals the sum of the anti-clockwise moments. They balance out entirely.
Just picture a perfectly balanced seesaw at the park. It's not moving up or down, and it's definitely not tilting left or right. That physical harmony is equilibrium. It literally means the object has 0 linear motion and 0 rotational motion. The resultant force is 0, and the resultant moment is exactly 0.
All right, on to section 4, center of gravity and stability. Since we're on the topic of balance, let's talk about why things tip over and how we can prevent that. Have you ever tried balancing a ruler perfectly on your finger? That exact balance point right in the middle is its center of gravity. In physics, we define this as the single theoretical point where we imagine the entire weight of an object is concentrated.
And you see engineers taking advantage of this all the time. Just look at sports cars. They are deliberately designed to sit as incredibly close to the ground as possible to keep their center of gravity low. It's an engineering trick that keeps fast cars glued safely to the road during high-speed turns, drastically improving their stability so they don't flip over.
So this whole center of gravity thing completely dictates an object's stability, which we break down into 3 categories. First up is stable equilibrium. This is when an object gets a slight push or disturbance and it naturally rocks right back to its original position. It actively wants to stay balanced. On the flip side, we have unstable equilibrium. If you bump an object in this precarious state, it's not coming back. Instead, it moves farther away from its original position. It essentially just topples right over. And finally, neutral equilibrium. Imagine a ball just sitting on a flat table.
If you push it slightly, it just rolls and settles perfectly wherever it stops, staying in equilibrium at its brand new position. Let's wrap things up with Section 5, Real-World Physics in Action.
Okay, we've gone through the theory, but turning forces are literally all around us in the real world. Using a spanner or wrench to loosen a tight nut, pushing down on a bicycle pedal, turning your steering wheel, even a playground seesaw, cutting paper with scissors, or lifting a wheelbarrow. Every single one of these items relies entirely on that magic relationship between the applied force and the perpendicular distance.
Let's actually run the numbers on a real example, just like you'll need to do on an exam. Step 1. Always identify your given values. Let's say force is 20 newtons and distance is 0.5 meters. Step 2, you apply the formula. M equals F times D, so 20 times 0.5. And step 3, state your result with those correct units. The moment is 10 newton meters. Nice and simple.
So let's do a super quick recap of your main takeaways for Chapter 4. The turning effect is the moment of force. The formula is M equals F times D. The SI unit is the Newton meter. Your pivot is that fixed rotation point. The principle of moments is your key to balance, where clockwise equals anticlockwise. And finally, the center of gravity dictates the stability of the entire object.
Now, before we go, I want to leave you with a bit of a brain teaser. We know exactly how a basic seesaw balances with just 2 people, but how would you calculate the exact equilibrium if, say, 5 people all sat on that seesaw at totally different distances from the pivot? Ponder that one for a bit because it perfectly sets up our next explainer where we'll dive right into solving complex, multi-force numerical problems just like that. Until next time, keep exploring the physics hiding in your everyday life.